Hi, I am Sukrut Rao from the Max Planck Institute for Informatics. I will be presenting our paper Adversarial Training Against Location Optimized Adversarial Patches. This is joint work with David Stutz and Bernd Schiele. I will first provide a short overview of our work, which will be followed by a more detailed presentation. A well-trained image classifier can accurately predict the class label for an image with high confidence. However, it is possible to construct a patch of pixels which when placed on an image causes the classifier to fail. This is known as the adversarial patch attack. Adversarial training is a defense mechanism where a network is trained with adversarial examples to make it robust against them. In our work, we perform adversarial training to defend against adversarial patches and show that it can improve model robustness against such attacks. An adversarial patch attack may be more effective on some image locations than others. Finding the optimal location on an image would make the attack stronger. For this, we devise a simple location optimization scheme to jointly optimize path location and values when performing the attack, and find that this leads to a stronger attack. We then perform adversarial training against this stronger attack and show that this in turn leads to a stronger defense, resulting in a more robust model. I will now present our work in detail. First, I will outline the objective and contributions. Then, I will describe the adversarial patch attack procedure, followed by the use of adversarial training against such attacks. Finally, I will provide a brief overview of the experimental results. An adversarial patch is a small contiguous patch of pixel values generated to cause a classifier to misclassify when placed on an image. Unlike imperceptible attacks, it is more practical since such patches can be printed out as stickers and placed in the real world. Such attacks could be an important consideration for applications such as navigation systems of autonomous vehicles. The objective of our work is to assess the effectiveness of adversarial training against adversarial patch attacks. We first propose an attack strategy that jointly optimizes patch values and location. Then we evaluate the performance of adversarial training as a defense against such attacks. For using adversarial training, a desired property is to have the strongest possible attack for each image. This is because a network trained using examples resulting from a strong attack can be expected to be also robust against weaker attacks. To achieve this, we make the following design choices for the patches used in our attack. First, the patches are image specific, with a separate patch tailored to each individual image. Such attacks have been shown to be stronger than universal patch attacks. Second, they are untargeted. That is, we only optimize the patch to push the prediction of the classifier away from the true class and do not try to force it to predict any specific alternative class. Third, they are location optimized, where we use a heuristic approach in an attempt to approximately find the optimal patch location. Optimizing path location can be helpful since not all path locations may be equally effective. We would like to find that location for any image where the attack is the strongest. However, at the same time, we would like to ensure that the path does not completely occlude features of the image that are vital for the classifier to classify accurately, since such an attack would not be very interesting. As an approximation for enforcing this, in our location optimization scheme, we allow patches to be placed anywhere except in the center of the image. Next, I will describe the settings used for specifying the patch location. First, we use two strategies to decide the initial location of the patch at the start of the attack procedure. The first is to place the patch at a location near a corner of the image and keep it fixed there throughout the attack. This also serves as a baseline to compare against the use of location optimization. The second is to place the patch at any random location on the image, as long as it does not intersect with the designated center region. With this initialization, we consider both the case of keeping the patch fixed as well as optimizing the location. Next, to optimize location, we use a simple approach. We check if a location in the neighborhood of the current path location is better. This is done by moving the patch to each location in the neighborhood and checking if it is more effective, that is, if it leads to a higher classification loss. If such a location exists, the patch is moved to that location. Based on the definition of neighborhood, we use two approaches. In the first approach, full location optimization, we search by moving the patch by a fixed number of pixels in each of the four directions: up, down, left, and right. In the second approach, random location optimization, we search by randomly selecting a direction in each step and only checking along that direction. This may miss some opportunities to improve path location but benefits from a lower computational cost. since it requires just one additional forward pass to the network as compared to 4 additional forward passes for full location optimization. The following is the optimization function for the attack. The patch is defined by delta, that represents the perturbations or patch values, and m, that represents the mask, which indicates the path location. The goal is then to find delta and m that maximize the cross entropy classification loss of the network. Finally, the following is the attack procedure. The patch is initialized with random values and placed either at a fixed or random location. Then, patch values and location are optimized in alternating steps. Next, I will show a visual example of the attack procedure where the patch is placed at a random location and optimized using full location optimization. We have an input image and a train classifier which gives the following output. Let us assume that there are only 4 classes to predict from, and here dog is the correct class. The plot on the right top shows the classification loss, and the plot on the right bottom shows the confidence of the network for each class. The first step is to initialize the patch, which is done at random, and it is then placed at a random location outside the center region as shown. Then, in the first iteration, we perform a forward pass. This may lead to a small increase in loss due to it blocking parts of the image, but in general, this in itself is not enough to cause a misclassification, as the classifier is usually robust to small occlusions. Then, we perform a backward pass and compute gradients and update the patch values. Next, we perform the location optimization step. We first move the patch up by a fixed stride, which in this example is 1 pixel. We then perform a forward pass and compute the loss as shown. Next, we move the patch right by 1 pixel. Once again, we perform a forward pass and compute the loss. We repeat this for all 4 directions. Note that the loss need not always increase. Finally, we choose the direction that led to the highest loss increase and move the patch in that direction. In this case, we move the patch right. In general, it is also possible that no direction leads to a loss increase, in which case the patch is not moved at all in that iteration. This ends the first iteration. In the second iteration, the patch values are again updated, followed by a location optimization step. We first move up as before. But in this case, we do not move right, since doing so would cause the patch to intersect with the center region. This is skipped and we move on to the next step. Again, at the end, the patch is moved in the direction of the highest classification loss, which is up in this example. This is repeated for several iterations. At the end, we have obtained an image with an adversarial patch that in this case has been successful in causing the network to misclassify this image of a dog as a cat. The location optimization procedure is only an approximate heuristic and would likely not allow the patch to move very far from its initial location due to the presence of local optima. Moreover, the patch is initialized and placed randomly. To smooth out the effects of randomness, we run the attack several times and select the path that leads to the highest classification loss. So we have the input image, the attack algorithm, and the patched image. This is repeated several times. And the image leading to the highest classification loss is chosen, which is the third image in this case. This concludes the description of the attack procedure. Next, I will describe the procedure of adversarial training against this attack, which we refer to in short as adversarial patch training. The objective is to train the network so that it is able to correctly classify both clean, that is unattacked, as well as adversarially patched images. To do this, we use the following optimization function that optimizes weights to minimize the loss. The first term corresponds to optimizing for adversarially patched images, while the second corresponds to optimizing for clean images. To jointly optimize for both, we attack half the images in each batch in training and use clean images for the other half. Next, I will describe a visual example of the adversarial patch training procedure. The following is a batch of 4 images along with their true labels. And this is the attack algorithm, which uses the current iteration of the train network to generate adversarial patches. We pass half the images through the algorithm and obtain patched images for them. This is the attack step. The network is then used for the training step. The batch of images is passed through the network and we obtain predictions. Initially, even for a trained network, many of the predictions for adversarially patched images will likely be incorrect. We then perform a backward pass and update the weights, training the network to correctly classify patched images. This network with updated weights is then used by the attack algorithm for the next iteration. This procedure is repeated for several iterations, and we finally end up with a network that is robust to adversarially patched images. This concludes the description of adversarial patch training. Next, I will provide a brief overview of the experimental results. The following is the setup. We perform experiments on the CIFAR-10 and the German traffic sign recognition benchmark datasets on a ResNet-20 network architecture. We use 8x8 sized patches on the 32x32 sized images. This is because this was the size when the robust test error of a normally trained network, which is the classification error on adversarially patched images, saturated. This can be seen in the figure on the right. We use 4 attack configurations. With a patch at a fixed location called AP fixed, with a patch at a random location without location optimization called AP ran, with a patch initialized at a random location and optimized using random location optimization called AP ran LO, and with a patch initialized at a random location and optimized using full location optimization called AP full LO. Then, for each of the attack configurations, we train a model using adversarial patch training and obtain 4 models: AT fixed, AT ran LO, and AT full LO respectively. The computational effort for performing the attack in terms of the number of iterations times the number of attempts is different when training and evaluating. For training, this is set to be 25, while for evaluating, this is set to be 3000. This is because training is more computationally intensive. Using a much stronger attack for evaluation also increases confidence in the robustness results for each model. I will now present some of the results on CIFAR-10. Further results can be found in the paper. The following table shows the robust test error for each attack on each model. Normal refers to a model trained without adversarial patch training. We see that given the attack effort, every attack is nearly 100% successful against the normal model. The AT fixed and AT ran models show some robustness against the attacks as compared to normal. AT ran performs better because it has been trained to defend against patches at any allowed location on the image. We also see that the attack strength increases from left to right, with the attacks using location optimization performing the best. Finally, the AT ran LO and AT full LO models perform the best, with AT full LO performing substantially better. This shows that full location optimization is very helpful in improving the effectiveness of adversarial patch training. This table shows the clean test error, that is, the classification error on unattacked images for each model. We see that adversarial patch training, while improving robustness against patched images, does not decrease accuracy against clean images. Finally, the following figure shows heat maps of successful attacks with full location optimization across 1000 attempts for a single image on each model. For normal, we see that it is spread nearly uniformly across the allowed region, indicating that attacks are successful nearly everywhere. However, for the other 4 models, we see that adversarial patch training reduces the region where the attack is successful, and only patches at certain locations are successful in fooling the network. In this particular example, for the AT full LO model, none of the 1000 attempts were able to generate a patched image that could fool the network. To conclude, in this work, we proposed an adversarial patch attack strategy with location optimization. We showed that location optimization strengthens the attack, and finally, we showed that adversarial patch training with location optimized patches improves model robustness. The following are links to the paper, code, and contact information. Thank you for your attention.